Hi everybody. This is the second part of our lecture on Chapter 1, Propositional Logic. So last time we left off on truth tables, and we completed the truth table here for the propositional logic statement right here. And this was the completed truth table. And yesterday in our discussion, we had a second example where this is right straight from the discussion notes, this stuff here. Complete the truth table for this propositional logic statement. And here's the completed table here. And you notice that at the end, it turned out that this propositional logic statement is always true. And a statement like that is called a tautology. Okay, tautologies play an important role in propositional logic. And I would like to go over some well-known. So let's even look at another one. Let's look at another one, see if I can fit it on the same page here. Come on. Alright, so here's another tautology. And we'll see that it's a tautology by making its truth table. So show that the following is a tautology. Using a truth table. And the statement is that P implies Q is logically equivalent to, so don't need the parentheses there, P implies Q is logically equivalent to P naught or Q. So here we've only got two propositional variables. So the truth table only needs 4 rows. So 1, 2, 3, 4. So we've got P, we've got Q, and the 4 truth possibilities for P and Q are as follows. 2 true, 2 false, and then alternating true, false, true, false. So this is all 4 2 times 2 possibilities. So we've got P naught, so in that statement, so by operator precedence, that's evaluated before anything else. So P naught is false, false, true, true. And then P implies Q, and P naught or Q would be evaluated second and third, or third and second, or this second and that third. So P implies Q. Well, the only time P implies Q is false is when the hypothesis P is true and the conclusion Q is false. So in row 2 it's false, and it's true everywhere else. Here, the only time P naught or Q is false is when both P naught and Q are both false. So that happens in row 2. So that's false here and true everywhere else. So now, the final row for the final column for the logical equivalence. Logical equivalence is also logical equality. This can be thought of as sort of an equality symbol in propositional logic or in Boolean algebra, Boolean arithmetic, excuse me. This is true. Double implication is true when these are both true or both false. Well, here we have that they're always the same. They're both true in 3 rows, both false in 1 row. So this is always true, and therefore that's a tautology. So that's one well-known tautology. Here are some other ones. So that one that we just did is called the implication tautology. And that is that P implies Q is equivalent to P naught or Q. Another one is contrapositive. The contrapositive tautology is that P implies Q is equivalent to Q naught implies P naught. Right, so P implies Q is not the same as Q implies P, but it is the same as Q naught implies P naught. Associativity. These are actually 2 tautologies. A or B, A disjunction B, disjunction C, is the same as A disjunction B, disjunction C. Right, I mean, this is because essentially disjunction can be defined for 3 or more terms. You don't really need parentheses. But if you were to, just define it strictly with 2 terms, then these are logically equivalent. Same thing with conjunction. Right, so that's the associativity tautologies. Next, distributivity is a little more interesting. A and B or C is logically equivalent to A and B or A and C. So conjunction distributes over disjunction, right? Like multiplication distributing over addition, right? This is A and B or A and C. But you also have the other distribution as well. A or B and C is logically equivalent to A or B and A or C. Distributivity tautology. Commutativity. These are kind of boring. A or B is logically equivalent to B or A, obviously. A and B is logically equivalent to B and A. Now, of course, one has to actually create a truth table to show that these are tautologies. But we already did one. I mean, you could maybe do one of these, the distributivity ones, to show that these actually are tautologies. Okay. Commutativity. What's next? Double negation. A lot of these are kind of obvious. Commutativity is obvious. Double negation is obvious. A naught is logically equivalent to A. This is an important one. De Morgan's laws. A and B naught is logically equivalent to A naught or B naught. And A and B, or A or B naught, is logically equivalent to A naught and B naught. One of these is actually written into the English language. It's this one here. This one is a little bit like the neither nor construction, right? If you want to say, it's not true that you can eat. It's not true that we own a car or a boat. It's not true that we own a car or a boat. So that's what this is. No automobile. It's not true that we own an automobile or a boat, right? It's not true that we have an automobile or a boat. That's like saying we have neither an automobile nor a boat. So nor isn't or. Nor is not or. So it's actually conjunction. Not or is actually a conjunction. We don't have an automobile and we don't have a boat, right? If it's true that we have, if it's true that we don't, sorry, if it's false, if it's not true that we have an automobile or a boat, that means we don't have an automobile and we don't have a boat. And the way we kind of say that slickly in English is we have neither an automobile nor a boat. That means not an automobile and not a boat. So that's De Morgan's laws, and this one is actually the neither nor construction in English. So De Morgan's laws, there's a few more. So just some notation, here's one. Idempotent. A or A is logically equivalent to just A by itself. A and A is logically equivalent to just A by itself. Complementation looks like this. A or A naught, right? A or A naught. That's always true. It's a tautology, in other words, right? And we write that like this, right? Where one means a tautology, right? A and A naught. That's logically equivalent to 0, where 0 means, right, you don't say T or F, I mean, tautology means true, and where 0 means false, right? So A and A naught is logically equivalent to false, because they can't both be true. A or A naught is logically equivalent to true, because at least one of them is true. That's called complementation. And now that we've got the 0 and the 1, we have the identity tautologies, which are that A or 1 is, A and 1 is logically equivalent to A or 0 is logically equivalent to A, and we also have the annihilation tautologies, which is A or 1 is 1, and A and 0 is 0. And that's it. Those are sort of the basic tautological equivalences. So tautologies that are logical equivalences or double implications. So implication, contrapositive, associativity, distributivity, commutativity, double negation, De Morgan's laws, idempotent, complementation, identity, and annihilation. Now, what you can do is you can put these tautologies together and to create larger tautologies. So these tautologies are sort of like rules of Boolean arithmetic. So these tautological equivalences can be combined to prove that other tautologies are in fact, that other statements are in fact tautologies. Think of these as equivalencies as rules of Boolean arithmetic or Boolean algebra rather than the algebra of real numbers. All right, so there's some rules of real numbers and algebra that you use, and this is a new set of rules for Boolean algebra. So for example, show that the following is a tautology. A implies B implies C is logically equivalent to A and B implies C. Okay? So do this via a chain of logical equivalences. Not stacking equations, but a chain of equalities. And by equality, I mean this thing. Right? That's equality in logical terms, in logical values. All right. Well, A implies B implies C is logically equivalent to via the implication tautology. The implication tautology, right, was that P implies Q is logically equivalent to P naught or Q. Right? So this one here is going to be A naught or B implies C. Right? A implies B implies C is equivalent to A naught or B implies C. So I'm thinking of the A as P and this thing as Q. So this is P implies Q. So then this is P naught or Q. All right, let's do it again. Also by the implication tautology, this B implies C is B naught or C. And then by the associativity tautology, right, this is A naught or B naught or C. That's the same as A naught or B naught or C. Right? And then by De Morgan, A naught or B naught becomes A and B naught or C. Right? A naught or B naught is A and B naught. And then the or C is still there. And then the implication tautology again. Alright, the implication tautology was that A implies, well, let me use P and Q. P implies Q is logically equivalent to P naught or Q. So here we have P naught and Q, or Q. P naught or Q. So that's logically equivalent to P implies Q, right? Which is what we wanted. So this is equivalent to this, is equivalent to this, is equivalent to this, equivalent to this, is equivalent to that. So the first is equivalent to the last, and that's what we wanted, right? A implies B implies C is equivalent to A naught and, or sorry, A and B implies, it's not Q, implies C. All right. So we'll have some more examples of that, but there's a nice one right there. Now, one could also show this is a tautology by using a truth table, right? It's a truth table with only 8 rows to it. You only got 3 propositional variables, A, B, and C. So you have 2 to the third equal to 8 rows in your table. So one could do it that way. But as the number of propositional variables grow, like if you've got 4, 5, or 6, if you have 6 propositional variables, and your truth table is going to have 2 to the 6, like 64 rows. So it gets a bit unwieldy. So doing things in this algebraic fashion can be preferable. Okay. Translations of English language statements. Into propositional logic. Okay, so let's just jump right into some examples. Okay, so for example, let H be the proposition, the horse is fresh, not tired in other words. K equals the knight wins. And A is the proposition, the armor is strong. So here's a bunch of sentences. Let's translate them into propositional logic using these statements here. A. If the horse is fresh, then the knight will win. Well, this is just the standard form for implication. If the horse is fresh, then the knight will win. All right, that's the classical, one of the 2 classical ways in which implication is written. If, then, all right, if H, then K, or H implies K. B. The knight will win only if the horse is fresh and the armor is strong. So the connector here is only if, the main connector. The main connector, or in this statement here is this. Right? This is the secondary connector. All right, K implies H and A, or H and A implies K. So this is either H and A implies K, or K implies H and A. Which one is it? Well, remember how we described implication. Instances where horse is fresh and armor is strong is contained in instances where the knight wins. That's this statement. This statement is the knight wins. Instances where the knight wins are contained within instances of horse is fresh, and armor is strong. So what you do is, if you're having a hard time deciding which one it is, look at one in the gap here. This is an instance of right? The knight wins. And H and A is false. The knight wins, but either the horse is tired or the armor is damaged or whatever. Okay, the horse is tired or the armor is damaged. Here is an instance of the horse is fresh and armor is strong, but the knight loses. The knight loses anyway. Which one contradicts the English language statement? The knight will win only if the horse is fresh and the armor is strong. The knight will win only if he's got, good horse and armor. So here the knight wins, but either the horse isn't good or the armor isn't good. Does that contradict this? Yes. It does. The knight will win only if, he's got both H and A. Here, the knight's got H and A, but he loses anyway. Does that contradict this? It says the knight will win only if the horse is fresh and armor is strong. Not that if he's got a good horse and good armor, he's going to win. I mean, maybe it's his first tournament and, everyone else is a veteran. So he's still going to lose, right? So it doesn't contradict this statement. This instance does. The knight wins, but he's got a tired horse or weak armor. So this one is incorrect. So this one contradicts the English statement. So the correct translation is K implies H and A. Right? The knight will win only if the horse is fresh and the armor is strong. Right? So knight is contained within H and A. The knight winning is contained within instances of H and A. So only if the horse is fresh and the armor is strong will the knight win. Alright, that was B. Now, is there an easier way to do it? No. You just have to go through those motions if you're having a hard time seeing which containment it is in that statement. The knight will win only if the horse is fresh and the armor is strong. So when you're saying only if, right, it snows, it rains only if it's cloudy. Right? It rains only if it's cloudy is a similar statement. It rains only if it's cloudy. Right? That means that instances of rain are contained within instances of cloudiness. Right? Instances of rain are contained within instances of cloudiness. If you look at something here, this is an instance where it's cloudy but it's not raining. Right? If it's raining, it rains if it rains only if it's cloudy. Doesn't contradict that it can be cloudy but not raining. The other way around, right? It rains only if it's cloudy. Here's an instance of it's raining but it's not cloudy, right? So that's an incorrect statement. So this is the one. It rains only if it's cloudy. So the only if construction, keeps the propositions in the correct order. It rains only if it's cloudy. In other words, if it's raining, then it's cloudy. Right? If the knight wins, then the horse is fresh and the armor is strong. Or, if it's raining, it implies that it's cloudy. So it keeps things in the proper order when you use the only if. But to me, it's confusing because the if is here rather than here, which is the usual spot where it is. So I can't stand it when people say it because it always confuses me. So if, then, and implies are the best ones. All right, that was B. C. A fresh horse is a necessary condition for the knight to win. A fresh horse is a necessary condition, not sufficient, necessary condition. Right, so fresh horse, right, knight wins. This is fresh horse implies knight wins. This is knight wins implies fresh horse. Knight wins implies fresh horse. So a fresh horse is necessary. Fresh horse is necessary. In other words, if you don't have a fresh horse, you ain't going to win. So this is no good. Right? This is the knight winning with a tired horse. All right, fresh horse is necessary. So the knight can't win without a fresh horse. So this one is incorrect. All right? So K implies H. Knight implies knight wins implies fresh horse. D, a fresh horse is sufficient for the knight to win. A fresh horse is sufficient for the knight to win. So this is exactly the opposite of this one. So I'll just copy it over. So I shouldn't have that there. Oops. Come on. Ugh. A fresh horse is sufficient for the knight to win. Again, you get the same two possibilities. But which one is it? Right, a fresh horse is sufficient. A sufficient condition. Right, so here you got a fresh horse, but the knight loses. Right, so this one is incorrect. Right, you got a fresh horse, but the knight loses. This is an instance that the horse is fresh, but outside the instances where the knight wins. So that's incorrect. So this one is having a fresh horse will give you a win for the knight. Okay? Not that the knight can't win with a tired horse. He might. Okay, but it's not the correct one. Or sorry, but not that the knight can't win with a tired horse. Okay? That's not a contradiction. So this is the proper interpretation. All right, that's good for that example. And then one last topic within here is negations of, so it's related to this, of English language statements. So, for example, okay, write in clear English the negation of the statement if the restaurant is good, then the prices are high. So if the restaurant is good, then the prices are high. I want to write the negation of that in English. Now, in other words, write down the English language statement that has the exact opposite truth value of this. In other words, if this statement is true, write down the statement that's true when, write down the statement that's false when this is true, and true, and this is false. Okay, it has the exact opposite truth value. Okay, step 1. So, I mean, if you can't do it right off the bat, here's the steps to do it. Step 1, translate to propositional logic. So, if the restaurant is good, then the prices are high. Step 2, negate. Just take the whole statement and negate it. Now, use the tautologies to distribute this negation sign through. Step 3, simplify. Right, distribute the negation using those tautologies from before. So via the implication tautology, this is G naught or H. And then via De Morgan, this is, oops, I'm sorry, that negation is still there. G implies H is the same as G naught or H. Then using De Morgan and double negation, so this is implication, using De Morgan plus double negation, this is the same as G and H naught. And then rewrite back in English. Right, the restaurant is good. But the prices are reasonable. Prices are not not high. Not high could be reasonable. Right, the restaurant is good, but the prices are reasonable. That's the same as saying the restaurant is good and the prices are reasonable. They're the same thing, although but is maybe a little bit more appropriate here. It's conjunction, but it expresses some kind of like it's unexpected, right? It's a good restaurant, but it's not expensive, right? So you can either write it like this or write it like this. The restaurant is good, but the prices are reasonable. The restaurant is good and the prices are reasonable. Either or is correct. All right, let's try another one. If the restaurant is good, then the food is excellent and the service is great. Right? When you say a restaurant is good, it means the food is excellent and the service is great, both. That's what you mean. Or that's at least that's what the statement is claiming. But that's a matter of opinion, of course. It could be like, of course it is a value judgment and all that, but we're treating it as a statement in propositional logic. Maybe you don't care about service, you just care about the food. Or something like that. Okay, so translate into propositional logic. If the restaurant is good, then the food is excellent and the service is great. And then you're going to negate the whole thing. Right? So, like 20 years ago, about 20 years ago, it was kind of in style to say, like, this exact sort of thing. Like, you would say something that wasn't true, but you would say it as if it was true. maybe your parents or your aunts and uncles still talk like that or something, but you would say something like that. Oh, I really like that bicycle. Not, you'd say not at the end of the statement. That's what this is here, right? But we don't want to talk like that. We want to say it in more proper standard English. Okay, so you translate the statement into propositional logic, and then you add your not at the end. And now you want to distribute that not through the statement, simplifying that statement. So by the implication tautology, this is G not or F and S. And now I'm going to need parentheses here. Because or doesn't take precedence over the and. Now I'm going to use De Morgan and double negation. And this is going to become G and F and S. Not. Right? The or becomes an and. This gets negated. That gets negated. Now I'm going to use De Morgan again. And this is going to be G and F naught or S naught. Right, so now we can say it in English. You could use distribution if you want, but you don't have to. Translate this back into English. The restaurant is good. But, which is conjunction, the food isn't good, or the service isn't good. So this statement has the exact opposite truth value of the original statement. If the first statement is true, this statement is false. If the first statement is false, then this statement would be true. Okay, it has the exact opposite truth value, right? This statement is saying for a restaurant to be good, it's necessary that both the food and the service are excellent. But this person is saying the opposite. It's saying, no, the restaurant could be good with either, food that's not great or service that's not great. It's not necessarily that both are great. So it all depends on what you mean by good, right? So these are the exact opposite in meaning. Okay. How about an if and only if statement? How do you negate an if and only if statement? I forgot the double negation tautology. Double implication tautology. The double implication tautology is the following, is that P, if and only if Q, is logically equivalent to P implies Q and Q implies P. So P is contained within Q and Q is contained within P, so the only possibility is that P and Q are equal. So this is good for negating statements that say if and only if. So let's write the negation of the statement, the restaurant is good. Restaurant, I always want to put the U earlier, is good if and only if the food is tasty. The restaurant is good if and only if the food is tasty. So they're equivalent, right? That's what this person is saying. You know, goodness of the restaurant means that, you know, the food is tasty, and that's it. That's necessary and sufficient for the restaurant to be good. So, good restaurant if and only if food is tasty. So, we want to negate that. So, good restaurant if and only if the food is tasty. Negate it. So, by the double implication tautology, this is G implies F and F implies G. And we're negating that. Via De Morgan's law, this is G implies F not, or F implies G not. And to negate an implication, we've seen it a few times already. G implies F negated is G and F not, or F and G not. Now we can translate that back into English. Either the restaurant is good, and the food is bad, either the restaurant is good and the food is not tasty, or the food is tasty and the restaurant is not good. So the negation of if and only if is actually that exclusive or. One is true and the other is false. Right? Either G is true and F is false, or F is true and G is false. Right? That's the exclusive or. Okay, so that's it for the first section. So we've covered all of the material that's necessary for the first homework assignment. And we'll go over a few more examples in class for all of these types of problems, and then we'll move on to Chapter 2 after that. Okay, that is the end of the lecture on Chapter 1, second part.